The LPC is actually linear predictive coding technique, and it is used specifically for the speech analysis technique. So let me quickly write a point over here related to the speech analysis part. Okay, so LPC, right? It's actually a very powerful analysis technique, right? Just for the estimation of various parameters, we can use it. And if you store only those basic parameters, right? At any point of time, if you want to come back to the complete speech, yes, it is possible. That's why this is also can be considered as a compression technique. Okay, right. So but the original invention of this particular method was to do an estimation, right? So analysis technique, I'll write, it is used to estimate the speech parameters. So when the speech is generated, we have the following fundamental parameters related to speech. The first one related to the, okay, right, pitch. Okay, so the pitch is fundamentally, right, the frequency with which, right, somebody is going to speak, right? Then there is another version of the frequency. This is called as a formant. This is something like an enhanced version of the frequency. Okay, then the way the response of the vocal tract. Okay, vocal tract response, right? So this actually includes the mouth and the throat response. Okay, also you can do an estimation of the intensity of the speech. Normally this relates to the loudness with which somebody is going to speak, right? So these are the various, again, they're the fundamental ones, right? LPC can do even a lot of other approximations and estimations as well. But so the fundamental idea behind the LPC is that you can estimate this, right? These estimated values can be stored, right? And when you try to retrieve them, right, you are trying to do the synthesis of the speech. Speech can be generated from them. If you know these values, right, whatever you are trying to speech, whatever I am trying to speak, if you try to model them using the LPC coefficients, you can try to retrieve back. Okay, so that's the overall idea, right? You want to save or you want to transmit only the coefficient, right? Other side, on the other side, when you have a receiver with you, right, you receive the coefficients and convert them back into the speech. So you don't have to transmit the complete all the samples, right? You actually, you can see that the speech has been represented by lesser number of features. All right, so what is the use of this LPC? LPC actually provides you, right, the it's like a characteristic of LPC, right? So LPC, it provides a very accurate estimation, okay, of the speech parameters. This is the first very it's like a positive quality of the LPC, right? And also you can actually perform what is called as a uh, it supports selective speech related computations. In a sense, if which part of the speech you want to write, do a calculation of, you can do that, right? It's not like the whole signal you need to process. Selective, right? That's now. So what is the fundamental idea behind LPC? Now we try to represent the speech in the form of a linear combination. All right. So this was our idea in even in the previous sessions where we looked at the adaptive part, correct? So adaptive representation of speech we have considered, where we saw that we try to have a coefficient alpha that is adaptively changed according to the error present in the computation, right? So the how the error was generated, comparing the predicting the current sample from the past sample, right? So now also we'll try to do the very similar process, right? But it is going to be linear. There is no adaptive thing. Okay, so the principle of linear predictive coding. So fundamentally, we try to represent the speech samples in the form of a linear combination. So linear combination of what? Linear combination of the past samples, right? I try to represent the current sample using some past sample, let's assume. Okay, so the speech samples can be approximated as a it's a linear combination of past samples. So if you look at the representation, current sample is denoted by x of n. Past sample will be x of n minus k varying from 1 to any past value, maybe some p. I might have access to the past 10 sample, let's say. So p equal to 10 x of n minus 1, n minus 2, n minus 3, dot, 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 up to x2, x of n minus some number. Okay, so using those values, right, if you try to predict the current value, so predicted value being subtracted from the accurate exact value which is coming right now, that difference is what is called as an error, correct? So the point is that this error should be, you try to say when the error is minimum, we can say that okay, the prediction that actually occurred so far is good, right? Because error should be minimum, right? What is predicted and what exactly the speech data that comes, if they are completely different, right, then you cannot say your prediction is good, right? Okay, so what is important, I'll add on to the same point. Linear combination of the past samples by, right, okay, minimizing the error. This is very important. Okay, this is the fundamental idea, so we got it as a principle. Now how do you do this? In order to achieve this, what do you need? So uh, see, again, error can be defined in several ways, right? If you remember, we are using what is called as a sum of the squared differences, right? I'll take it normal difference, x of n and x cap of n, where x cap of n is the predicted value of the current symbol. All right, I'll take a difference, x of n minus x cap of n. I get an error. But you see, this error can be positive or negative, right? Both are possible. So in order to bring them onto the same side, like same polarity, you will simply square that, right? It's just an error square. Okay, so I got an error, I convert into positive by taking them into, by considering them into the square. Because you see, this is the problem. If at all, like, right, let me say I'm calculating error e is equal to, first number is positive, second number is negative, third number could be positive, second next sample you calculated could be a negative error. Now you see the actually error, actually whenever you add it increases, whenever you subtract it decreases. So you don't get actual picture of the error, right? What is the magnitude of error, you are not able to calculate here because you are subtracting error also, right? Error, whenever I do this, right, these things, right, plus e2 minus e4, you will see that error reduces, but actually it's not reduces. Error is there and error is negative, that's all. So in order to, right, compensate that, I'll square every term. So this becomes plus minus e2 square is plus e2 square, e3 square plus e4 square. Now you see everything is positive and its magnitude is being recognized. Are you getting the point? So that's why we square it. So one obvious question, but so the most common ways of representing error is, one is RMS, root of mean squared error, right? So the squared error comes into picture just because of this. Other error is sum of the squared, SS, you might have heard of. Many there are variations of errors that you can represent, but all are right. Almost all are, not all, right? Almost all are squared errors because of this reason. All right. So now my point was, how do you identify? So in order to do whatever we mentioned in the previous point, right, it can be done by minimizing the sum of the squared differences. Difference in the sense it is there, okay, between the actual sample and the predicted sample, right? So to achieve this, one has to minimize. One has to minimize the sum of the squared differences between two things, right? What are they? Between the actual speech samples and the, predicted sample. So this is what we are going to call as sum of the squared error. All right. Okay, now let's look at the speech generation process. I think we have discussed this once, but let us try to make a simple model compared to the one we had discussed. Okay. So in order to understand the whole process, we need to look at the what is called as the speech synthesizer. So the one which generates the speech. Normally we have this is the model of our lung. Okay, the lungs is going to have, it's going to decide what will be the pitch frequency, right? Pitch frequency in the sense it is the frequency with which I speak, right? That's my pitch frequency. So that is determined by the periodic impulses generated by the lungs. All right. So just to model that, right, what we do, we'll use a first block that is called as the periodic impulse generator, right? I can actually model this program based on the programs or even the hardware, right? We can try to, so that's one part. So this actually, right, takes an input. Okay, there is a input to this particular block, and that is called as the pitch frequency. So coming to the human speech, right, irrespective of what is the loudness, right, the person may be talking louder or lesser or doesn't matter, right, irrespective of that, this pitch frequency remains constant. Right? So that's a fundamental characteristic of with which the impulses are generated by the lungs of that person. Okay, so that's why it's this is going to be fixed. Loudness, etc., are controlled by something else. There is a gain parameter coming at a later stage, right? That will decide whether you are talking louder or right, you're trying to be quiet or okay. So that volume control comes later. This is the frequency. All right. Again, right? You see, when we speak, there is a noisy component present in everyone's audio, right? Whenever somebody is going to speak, so that is generated by that. That actually that noise is also supplied by a noise generator circuit. Okay, when we try to synthesize the speech, this has to be done by a what is called as white noise generator circuit. Okay, when we do the same thing using a software, you will use a random number generator. Okay, for this purpose. All right, now both will generate its own what you call the samples, right? Both will generate the required type of samples. Let me say this is this is the output of the periodic part. This is the noisy part. Now what happens? Both of them uh, they get sampled by a particular device. Okay, so let's say so they both generate the samples simultaneously, but both of them will not be used by the vocal tract. Both of them will not enter into the vocal tract. Okay, vocal tract. So what enters into the vocal tract is there is a sampling device. Okay, we modulate that using a sampling device. So here, this is the one responsible for either sampling the noisy part or the periodic part. So when the signal comes from the periodic part, that is considered as the actual speech. Okay, in between the speech, when there is no voice sample, because when somebody is speaking, there may be a voice related to that. If there is a voice, right? So you see, when I say right, like that, the sir part has no voice. It's just a noise, correct? So you see, noise. Somebody is generating a noise. Somebody is all some part other part is generating the what do you call as the voiced part, like whenever you say etc, right? So it has a voiced part. Okay, so now you see we need both of them, right? Some part of the speech will contain the periodic impulse that actually is a part of our voiced speech, and some other part may be the noisy speech, right? Noisy part of the speech. Both are there, both have to be there in order to right, generate the proper speech, right? In the sense, if somebody is not able to generate both of them, then that is considered to be a speech deficiency, right? So somebody is not able to generate all the part of the speech properly, so that is considered as a deficiency. Now you see, I'll just mark like this. There is, in the sense, this sampler will move and touch, right, both the sides depending upon the requirement, right? So you can see this is moving here and there. To decide what comes from the top part, right, is the unvoice. Is it unvoiced? It's voice, sorry, because it is a periodic impulse generator, right? So that has a voiced speech. And what comes from the bottom? It's a noisy structure, which we call it as a unvoiced. All right. So whatever is sampled by uh, this part, correct? So there is a sampler circuit. Once it is sampled, now it is actually the speech samples, right? We have what is called as an amplifier. So this is the A, which I denote amplifier. So there is a gain provided by, right? It's the something like the loudness that's coming in the picture. Okay, so we have a C. This is the loudness. Okay, then it passes to the vocal tract. Okay, voiced, unvoiced we have, gain also we got. Then after you have you obtain certain amount of the gain, right? It will go to the what you call it, the vocal tract, and it gets modulated. So that is what we try to represent by using the speech filter. It's a filter. So since we are trying to pass the discrete signals through this, because it's actually, if you see, right, we already have sampled, right? So there is a sampling part present here. That means it is discrete after this, right? That's why I'm not writing the continuous representation. So I'll call this is some h of z. indicating that that is the discrete filter. Okay, so filter has one output. Okay, I'll write the output below like this. It provides an output that is the approximated speech sample, because you are synthesizing. It's not the speech generation what is happening inside our right our body, right? So now you see this, what exactly happens here. The selected voiced or unvoiced sound is actually provided with certain amount of gain, right? And then you have to model a filter so that you can try to simulate the effect of mouth, throat, nasal passage of the speaker, where the actual speech is. And now you say this is speech synthesized, right? I want to so something like the announcements in maybe the airports, right? They are synthesized. Okay, so it's like you give the speech parameters to a software which actually generates the speech, right? So that's the concept here. So synthesizer is going to do that job. So let me write one point about that. I think the block diagram is clear, right? Okay. The selected voiced or unvoiced, okay, doesn't matter, sound, it's a still sound, it's not speech. Okay, initially it will be a sound, right? That sound gets it passed passed through a filter. It passes through a filter, and which I can say simulates all the required effects of mouth, throat, as well as the nasal passage. Because some of the sounds, right? Mouth, we know don't use mouth, we use the nasal passage. All right, right. Again, this is so it has to be very accurate because you want to try to reproduce the exact speech of a person, right? Exact person. So input signal is filtered by this filter in such a way that, right, required letter gets pronounced in the exact same way as that person, right? So that's why the filters response is pretty important. Okay, so I'll write that point as well. The input signal, in the sense it's a sound, right? It's not speech. The input signal is filtered. So filtered by a filter that is denoted by h of z in the z transform. Okay, in such a way that such a way that the required letter gets pronounced. That's all. That's the important part. Now, so we wherever we use a synthesizer, right? The synthesizer means whatever block we have written earlier, because this speech synthesizer will be used in the predictive part of the LPC as well as the in the sense the transmitter part. At the same time, it is being used even on the receiver side. Both side we use the speech synthesizer. Okay, so because of that, right, what is that synthesizer doing? I wrote a diagram just now. Okay, so now what we do, we'll directly go to the encoding part, okay, or even the transmitter part, anything is fine. Encoder is simply we call it as encoder when our intention is to save the speech in a compressed form. Okay, at the same time, if you are trying to send the speech, right, like our mobile phone, etc., LPC itself is being used. Okay, so but slightly advanced version of not what we are studying here, slightly advanced version. Okay, but still, right, it's a very what you call very sophisticated tool, right? It's a the compression happens by a huge amount. All right, so what we are going to see now here is the LPC. I'll write maybe this is a encoder, or it can be a transmitter. So directly now, in order to perform this encoding, we need the speech signal, right? So that is denoted by x of n speech samples. So samples are collected. So first part is called as an analyzer. Okay, so that is analyzer side. Now, so analyzer provides the certain outputs, okay, and this output is considered as the parameters, whichever we wanted to use for our encoding purpose. All right. So what we do here, we'll get the outputs of this as the parameters. Okay, and those parameters are going to be used to give as input to the synthesizer. Okay, so with synthesizer we already have seen, right? So I try to make an estimation of this x of n inside the synthesizer. Okay, so it actually provides certain parameters. So let me mark the parameters here. So these are the estimated parameters directly given to the speech synthesizer. So there is an analyzer part followed by a synthesizer. Okay, analyzer basically provides the speech parameters. Okay, now we got certain parameters. We'll use it for another purpose as well. So I'll take a signal from this point at a later stage. Okay, now this synthesizer, I need to generate an error, right? Because you see, this actually makes an approximation, right? So whatever you get here is basically, if you remember, this is the approximated x cap of n estimation. So what I do, I'll take, right, a difference. I'll use a summer block summation, and we'll try to take a difference, right? What difference I'm trying to take, right? I'll try to take this signal, and I'll bring that down. Now you see, this is from the actual signal I subtract. Okay, so we subtracted. Now this generates what is called as an error signal that I'm going to pass it through the ELPC encoder. This encoder gets another signal as well as that also has input. I'll show you. Okay, so this has two inputs. One input that basically comes from here. Okay, that is the error signal, right? I'll try to write it as E of n, error, and this using the pre-generated speech parameter. So I use the speech parameters which are generated. I'll give both of them as input so that this generates a set of outputs. Okay, so this is the LPC, Linear Predictive Coding output. So let me just check the diagram once again. So speech signal is given, it is speech analysis, fine. So generates the encoded, passed to the speech synthesizer, generates the synthesized or the approximated signal x cap of n. X of n comes from the top, take a difference between x cap So you get a E of an error. Use the error plus the parameters to the encoder, right, which generates the LPC output. So this is the fundamental block diagram. Okay. So if we want to write few points quickly, then this should be the case. Okay. So normally the sampled values are applied to the analyzer, okay, which analyzes them to determine the speech parameters which should be given for the synthesizer. So that will be our first point, right? I'll just write 2 or 3 points, then you can expand as required. Okay. So the sample, in the sense values of speech, are applied to the analyzer, which performs the analysis to determine the speech parameters. All right. So once the parameters are obtained, right, we will use them to the synthesizer, and the synthesizer reconstructed the approximated signal, right? The speech synthesizer generates the approximate speech. I'll denote it as x cap of n by using these parameters, isn't it? Okay. So the next point is that this is given, right? The error signal which is generated by the subtraction of by taking the difference of x of n and x cap of n is given as, right, the error. Okay, that error is given as input to the encoder. Normally we compare the sample signal to the approximated signal. Encoder forms the digital signal, right? So encoder's output will be discrete and digital in nature, and we call it as a LPC output, right? So using error E of n equal to x of n minus x cap of n, and the extracted parameters, extracted speech parameters. By using them, what happens now? The encoder, okay, by using this, the encoder forms LPC output in a digital format, discrete in nature. That's it. Okay, so that's the working of what is called as the LPC encoding or the transmitter. All right, next we'll look into what is called as the LPC decoder, or it is the receiver side if you are using it for a transmission. LPC receive. Right. So again, it begins with the reception or retrieving. If at all you saved the speech in the memory, right? You will save it in the form of the LPC coefficient you got, correct? Once you have that, right, it's in the memory, and you want to listen to somebody's speech, right? What you have to perform the reverse operation that has been carried out in the transmitter or the encoder part. So I need to do the decoding. All right. So I should start with the LPC. Okay, LPC input. So we'll take an input. Right. So look at the transmitter part, and what is the last block you see? It's an encoder. So I will perform the reverse operation of that by using what is called as a decoder. So every process needs to be reversed. Okay. So input to the encoder was the parameter. So now the decoder should generate the parameter, right? So what happens now? This generates two signals. Okay, one signal, right, will be the x cap of n, and the other part should be the error signal, because error signal was input to the encoder. So decoder should generate the that as an output, because it's a reverse process, correct? So now you see the decoder generates two signals. One of them is the error e of n, and the other signal is the x cap n, right? That needs to be generated from the parameter. So it generates the speech parameters, right? It is simple, because previously used to for an encoder e of n and the parameters were input. So decoder should do the reverse job, so it should generate e of n and parameter. Okay, so recall where the parameters, right, were used earlier in the synthesizer. So I'll give these parameters to the synthesizer again. Okay, so this is the speech synthesizer. Okay, I'll pass on these parameters to the synthesizer. So synthesizer generates an output. Let me directly take that to say over here. So I need once again a summer block, but this summer is not going to perform the difference like previous case. It's simply going to add. Okay, so previously we did the subtraction. Now we should do the reverse by doing the addition. Okay, so error signal comes from here. This is what I'll write it as the x cap of n, right? X cap of n will be added with the error signal to get the x of n. Okay, x of n is there. Recall the similar question I asked earlier. I have a discrete signal and I want to convert that into a continuous signal, right? It's actually a reconstruction of from your sample. What filter you are going to use here? Sorry, audio is not. Yes, discrete to continuous, low pass filter, right? So it's a, so once you have that, you get back your signal denoted by x of t, right? So starting from the LPC, which is present on the left side, right? It actually, right, passes through each and every element we see here, right? So that we get the speech signal back. Okay, so now let's quickly write 2 to 3 points here so that you can expand them later. Right, now as we can see, LPC is given to the decoder, right? Or some of the authors will call it as a demultiplexer as well, because one input is given, two outputs are taken. Even it is a demultiplexer. Okay, doesn't matter. Don't get confused. It's the same, right? From the LPC, we try to separate the parameters and the error signals. Okay, so two separate error that is denoted by E of n and uh, speech parameters. Okay, in order to do this, the speech parameters, uh, we use a decoder. Okay, from where I didn't mention. So, parameters. Parameters from the LPC input. Okay, we use a decoder. I'll also write the other term, or the demultiplexer. The circuit. This is the first object. Now, as we understood that, this decoder generates two signals. One is an error signal, and other one includes all the parameters of the speech which we are trying to represent. Now, so the parameters will go as input to the speech synthesizer, which produces an approximated signal, right, or approximated speech signal that is denoted by x cap of n, right, from the parameters. Okay, so that will be our next point. From the parameters of speech, the speech synthesizer produces an approximated signal. So let us denote that as x cap of n as shown in the block diagram. Okay. Next, what happens, you can see in the given block that this x cap of n is added with the error signal to generate the sampled speech x of n. So we can write that the approximate x cap of n gets added with the error. So error is denoted by x of n to generate the we call it as the sample signal. Okay, sample, or it's a discrete speech signal that is denoted by x of n, right? So in order to construct the in order to come back to the continuous domain from the discrete domain, I have to go for a reconstruction filter, which is LPF, right? So we use the low pass filter as a reconstruction filter. Okay, as a reconstruction filter to obtain the continuous speech the discrete speech. So this is what happens inside the receiver. All right, now let's quickly look at what are the various applications. Right, so the first application is inside the MPEG. Anyway, we as of now we have seen that the audio. I'm going to write about the audio part later. It's widely used even in the MPEG 4, right? Type of the encoding technique. Right. Then there is another name, another what you call audio encoding technique called FLAC. Have you heard of this? uh, some of the audio files which you may download from internet will be in this format .flac. Okay, so this is called as the free lossless audio. Good. Okay, FLAC stands for that. Inside that we use this LPC, right, in a slightly modified. Okay, then there are various what you call as the coding systems, we call it as a Kodak. Okay, various codecs are there, audio codecs, etc. Right, so in there, for example, like such as silk, etc. Right, and we also have something called as the, okay, this is the tonal analysis of various musical instruments. So this is also a major application, because whenever the musical instruments are actually being produced by maybe inside the factories, right, they have to make sure that the expected tones are coming out of the musical instruments. This is something like maybe specific, very specifically I'm talking about the ones which contain the strings, right, violin or any other, right. So where you see that, right, it the strings should be capable of, whenever you excite that, it should generate a specific frequency. So it's called as a tone, right. So that, whether you are able to generate or not using a specific this thing, for a given musical instrument, is it possible to generate the exact frequencies or not, right? In order to understand that, we can use the this LPC.